In this video, we'll use the Rice theorem and consider some applications of Rice's theorem. Rice's theorem is a powerful tool to prove that certain problems are undecidable if these problems relate somehow to the I/O behavior of Turing machines or to the languages that are accepted by Turing machines. For example, we know, or we have the feeling, that the question, does a Turing machine halt on input 42 is undecidable. We already know that it's undecidable whether a Turing machine halts on the empty tape or not. So why should 42 be different? And in fact, it is not. And we can easily use Rice's theorem to prove it, because we can consider a set S of specifications. And in this set S42, we simply collect all the functions f such that the function f is defined for the input 42. So we take all the Turing computable functions that are defined for the input 42 and we collect them in the set S42. This set is apparently non-trivial. S42 is non-trivial because it is neither the set of all functions, because there might be functions, of course, that are undefined for the input 42, and it's also not the empty set, because there exists at least one function that might be defined for 42. So this set is non-trivial. So we know by Rice's theorem that it is undecidable whether a Turing machine computes a function that is in S42. So by Rice's theorem, it is undecidable if a Turing machine computes a function in S42. However, a Turing machine computes a function that is in S42 if and only if it halts on input 42, because that's exactly the definition, that it computes a function that is defined for input 42. If it's defined for input 42, it means the Turing machine must eventually halt, otherwise it would be undefined. So we have this correspondence that it halts on 42 if and only if the Turing machine computes a function in S42. So we can simply, by using Rice's theorem, directly prove that this question here is undecidable. We can not only use the function version, we can also use, for example, the language version and prove some other interesting properties to be undecidable. For example, the property, does a Turing machine accept a regular language? So you start with some given Turing machine and you would like to know whether this Turing machine accepts a language that could actually also be accepted by a finite automaton. Because then you don't need all the mechanics of the Turing machines anymore for this particular language. However, this problem is also undecidable, because you can simply consider the set SREG taking all the regular languages. So in this set SREG, we simply collect all the regular languages. This, every regular language is of course Turing acceptable. So this is a subset of the Turing acceptable languages. And it's apparently non-trivial because there are regular languages, and it's not the set of all Turing acceptable languages. So SREG is non-trivial. And as it is non-trivial, we can use the language version of Rice's theorem and directly see that it's undecidable whether a Turing machine accepts a regular language or not. So by Rice's theorem, it is undecidable. Decidable if a TM accepts a regular language. And these are just two examples that you can easily extend for a lot of other cases.